Next up is Nico Gonkurov. Nico's been with us before plenty of times, previously as SureChem, now taken over by MacMillan. I'm sure Nico will tell us all about that.
So my name is on the program, but I'm actually not giving the talk. For those of you who know me and have known my attendance here, that in itself is a significant development because before it really was only me who could give the talk. SureChem was acquired by MacMillan a few years back, now a year and a half ago, and we were part of a new MacMillan technology business unit called Digital Science. So one of the things we've been doing is building up our team, and Andrew is our cheminformatics specialist, as bioinformatics as well. And our talk today obviously is about ChemAxon name to structure, but what we're doing is we're revisiting a talk that I gave at this UGM 2 years ago, where name to structure was a very new emerging tool, and because we had extensive experience with the 3 other commercial tools that are available, we decided to do some benchmarking, and at that time the results were so promising, we decided we would license it, and shortly thereafter we did. For this talk, we're looking at the improvements that have been made since then, and I think that Alex and Doug and Medzi will like what we have to say. And without further ado, Dr. Andrew Hinton.
Thank you very much, Nico. So what I'd like to do is start off with a brief description of the data environment that SureChem works in and has found ourselves dealing with. And then I'll give you a very brief recap on the analysis that Nico alluded to that we presented in the US UGM back in 2009, and contrast that with the type of analysis that we're going to be performing, what we've performed on the latest but one version of the ChemAxon name to structure tool 5.4 in 2011, and looking at the various different metrics as a way of gauging the quality that we're seeing in terms of coverage, rates of agreement, and latterly we'll do a retrospective modelling of what we think the various contributions have been, the different versions since 2009 have actually given us, and then we'll wrap that up. So just quickly, SureChem at a glance. SureChem takes patent data and provides a combined structure and text searchable database of patent literature from all the major authorities back from 1976. So we process USPTO, EP, WO, full text patents, and then along with that we have abstracts from Japan and MEDLINE. When we store this in our database, what this looks like is that we get about 12 million unique structures coming from about 20 million patents all in all. And those structures have been indexed from both the claims, the descriptions, the titles, as they appear as basically text strings of chemical names. And the key thing is that we're able to update the SureChem collection within 24 hours of a patent being published. So if you're at all interested and think that's something that might be useful to yourselves in your work, then I urge you to visit our website at www.surechem.org, and it's very easy. My colleague Elizabeth Pivotu is in the audience here, and we have a stall outside where you can easily arrange a free trial to explore the different products offerings of the SureChem. So just to run through what we do, we take the patents as raw text documents. We then perform some pre-process indexing steps, and we then have our own proprietary entity extraction software, which basically, as the name suggests, looks for chemical-like terms in the text, and once we think we found a chemical name, we then perform some error correction heuristics on that, and then we, and uniquely I think, give those chemical names to 4, used to be 3, but we've introduced ChemAxon recently, 4 name-to-structure conversion tools. And that's the main focus of my talk today, is that because we have not just one name-to-structure conversion tool, but a handful, we're actually able to do some benchmarking, do some comparisons of the different performances that these name-to-structure tools give us. Once we've done that, we're then able to store the structures, we standardize and generate a fingerprint, and we use ChemAxon's JChem base to perform the structure searching, so we're able to do substructure similarity searching on it. We then do some validation, and within 2011 we're introducing some manual validation steps, and finally we're able to push that out to the web service or the web API. So briefly, to give you a flavour of what we're up against in this process, name-to-structure challenges. As Daniel and others have alluded to, there are a lot of OCR errors coming from the text of a patent document. You'll often find issues with transposed letters, letters being represented as numbers, insertion of strange special characters that really would throw any self-respecting name-to-structure tool off guard. There are also some chemical terms in patents that we're just unable to properly deal with, whether they're inorganic compounds or they're ambiguous in some way. Interestingly, there's a paper there which suggests that I think it's 26% of the chemical names in the literature are unacceptable in some way and unable to be converted into a structure. The basic message is that you get a lot of false positives and you get a lot of fragmentation issues when you're trying to do this exercise. So we've developed some name-to-structure correction heuristics. These basically involve both proprietary and third-party pieces of software that have been arranged in such that we're able to, first of all, deal with the name fragmentation, the insertion of erroneous white space into the chemical names. And having dealt with that issue the best we can, we're then able to go through looking at putting in some sort of automated spell correction techniques, allowing for input of external name lists as a verification step, and that basically tidies up the data such that we're able then to get into a position where we're able to give that chemical name within the body of the patent to a name-to-structure tool and see if we can generate a structure, because before that we would have a very poor attrition rate. So that was where we are. That's what was where we were today, and in a sense, that was where we were also in 2009. That central workflow hasn't changed that much, and so we were able at that point to do a small analysis on benchmarking in 2009. Back then, we were comparing version of ChemAxon's name-to-structure tool 5.22 and 5.25 on a corpus of about 900 patents, where we extracted the chemical entities, converted those names to structures using all 4 commercially available name-to-structure tools, and measured some key numbers, such as conversion rate, and you can see the number of SMARs that we were dealing with was about 55K. So in that analysis back in 2009, we showed that there was some overall conversion rates had improved between the two versions. They were up about 16% in the conversion rates. They were also unique conversions were up again about 50%, and what we term, and I'll come on to this a little bit later, the full tool rate of agreement was much improved as well. So it was a good story back in 2009, and what we wanted to do today in 2011 was just to see where the various version improvements had got us in terms of these key numbers. So our benchmarking set was a little bit different. It was much larger. We decided that we would take pretty much all our patents that we had in our database, which represented about 20 million documents. This gave us, on first sight, about 34 million. And then once we looked to convert these structures, we were down to about 17 million. And we've subsequently sampled some data, and we think, on average, when we do a sort of a document-by-document analysis, we think we get about a two-thirds conversion rate from given chemical name, we're able to convert it into a chemical structure using one or more different tools. So we then triage the structures to remove what we've termed non-pharmaceutical. So this is a very crude way of using Lipinski's term. So that gave us about 10 million structures, and then based on duplication, either through the structures or through the unique names, we get to a corpus of about 7.8 million, and that was what we essentially provided our analysis, our benchmark set. Key message that I just want to emphasize at this point is that I suggest that anybody who is using a single name to structure tool in any of their process is that they actually take a look at another one, because we found that actually by using multiple name to structure conversion tools, this yields us an average and additional 40% of conversions compared with a single tool alone. So this is quite important if your business is trying to get a structural searchable patent database. So this is quite a nice graph, I think. So of the close to 8 million structure names, this is focusing on coverage. So you can see that if you look at it broadly, you've got about a third of those names are able to be converted by all 4 tools, regardless of what they are. You have another third where at least 2, but perhaps 3, again, those chemical names will be converted by at least 2 or more names. But interestingly, you're left with a further and a final third of chemical names whereby only one of the 4 tools will actually be able to generate a structure for it. And interestingly, when we looked at ChemAxon 5.4, we see that actually it was pretty high up there, only second to tool 2 in its contribution. ChemAxon provided us with 7% of the total, which represents about 500,000 names in there. So I think that's quite a powerful message. Another way of looking at this is the kind of the Venn diagram. So on the left-hand side, this is the kind of overlap, if you like, of the 3 tool coverage, and this represents about 5 million names. And we see that actually these different tools provide different features. So tool provides us the breadth. It provides us quite a significant amount of coverage. We actually know of other attributes that tool 1 provides of, which we think is quality. It might not provide as many names, but the chemical structures that are produced, we've done some internal testing, and we think they're the genuine thing. Tool 3, on the other hand, provides the ability to recognize chemical names that are referred to in the literature in foreign languages, and still yet be able to convert them to a structure. So when we look to add ChemAxon's contribution, we see that there is a distinct overlap. I mean, 57% of ChemAxon's names that it was able to generate a structure for would overlap with the existing kind of pool of names and structures that we had on the left-hand side here. But again, there was this 7% where actually ChemAxon provided a unique way into the structures of the names represented in the text. So in terms of coverage, we were really happy when we saw those figures. So when we move on now, we're able to not so much focus on coverage, but look at rates of structural agreement. What we see is that when we look at the raw numbers of where you have the same name, gives you a different structure, or you have a same name and all the 4 tools together give you the same structure. And if you break that down in terms of each tool's contributions, what we've showed in this graph is that ChemAxon, like each of the other tools, provides a similar level of structural variation in the name to structure. Another way of saying this is that if a tool was providing very different structures given the same name, you would worry. Because yes, there is subtle variation perhaps between different names, they're ambiguous, we know that. But if over a large test sample set, you were getting very different rates of structural agreement for a particular tool, you would be concerned. And this is a good news that they're actually pretty much the same level of structural variation given the same name, same structure, same name, different structure type of analysis. The key message here is that this suggests that 1 in every 5 chemical names will at least give you 2 or more different structures available, and you've got to somehow make a decision which you have to choose from. We have our own sort of preferred priority ordering of how we take from that, but again, you're going to get kind of a many-to-many kind of scenario quite quickly. So we just wrapped that up, but before we did that, that type of comparisons of rate of structural agreement, we looked at the pairwise agreement, and this gave us a little bit of insight of how the different tools could be related to each other in a kind of a broad number-based sense. And it shows that this is showing the proportion of the number of names with the same structure between 2 tools that intersect each other. So if we just focus on what ChemAxon is contributing, we see that tool 1 overlaps with ChemAxon about 57% of the times where there's a name with the same structure. Tool 2, it's a little bit higher, 66 or 67%, and with tool 3, it's a little bit lower actually, it's quite a bit lower, it's less than 0.5%. And by measuring the frequency of matching structures, what you're able to do is in a broad way perhaps relate the different naming tools that we use to each other, to themselves. And what we like to think is that this type of analysis shows that ChemAxon is quite closely related in terms of structural agreement to the structures coming out of what we've named as tool 2, but it's showing a fair bit of divergence away from the commercial name to structure tool that we've labelled here as 2.3. And if you're interested in what the real names of what these tools are called, you can buy me a pint in the bar later, and for a certain price, we could do it. Yeah, 3 pints. You see, that's inflation for you. So, in terms of a recap, though our data sets were very, very different. We were talking about 900 documents in 2009. We're now talking about 20 million documents, and the structures that are perhaps more pharmaceutically relevant from those. We think we can, when we look at broad proportions, make some sort of statement comparing the 2009 analysis and to today's analysis. And we showed that we think when you look at the proportions that actually we found that 33% of compounds were agreeing with 4 tools. That's gone up. And between 5.22 and 5.25, we also saw an increase. And that increase is measured again and mirrored again when we come to compare it with 5.4 with ChemAxon and all the latest versions of the respective other name structure tools that are out there commercially. But on the other side, that we see that actually where there was a downward change prior to 2009 in terms of the unique tool agreements, the single tool contributions, that's gone up now. And what we think is in 2009 we came to the broad conclusion that this decrease in sort of percentages is likely to be due to the kind of convergence of the higher four-way agreement that we were seeing. Today that's slightly different. Some, but not all tools by any way are converging on each other, but there are some tools, one or two, that seem to be moving away in terms of the chemical landscape that they're able to recognize in terms of chemical names and generate a structure for. So this sort of leads me to the final type of analysis that we did. We basically took the 7% of chemical names that ChemAxon was only able to generate a structure for. And we wanted to ask the question, well, this was using 5.4. What would, if we were to use 5.35 or earlier versions, what proportion of those names today would we have been able to use? And this is a kind of a retrospective analysis of the improvements that Daniel and his team have been performing. And what we see really quite nicely is that as we travel back or in time from, I guess it was probably prior to 2009, where we're dealing with 5.22, we see that there is a genuine increase. Each version improves the amount of structures that we're able to generate, but we saw a massive, a huge leap in the difference in terms of 5.35 and 5.4. And we've yet to test the very latest, which is 5.5, but we're really hopeful, and I think Daniel was saying that you know, in-house they were making some big changes in 5.4, and that's been carried through to 5.5. So that's a really good news message that we're seeing significant improvements with one of our full tools. We're dealing with a lot of structures here, so we had to, if we wanted to get into any more detail, we had to really do some sort of kind of quick and dirty analysis. I mean, clustering and generating scaffolds is a difficult business, and this was a very kind of rough and ready approach that we did. But we wanted to understand whether the improvements we've seen in the graphs previously was related to a significant new introduction of chemical name space that wasn't covered previously, or was it something else? And what we did in this analysis is that we took the structures that only version 5.4 was able to give us the structure for, given its name. And we turned them into ring assemblies. These are sort of Merco assemblies. And then we clustered them, and we looked at the kind of the size of the clusters and the shape of the tail. And we found that actually there was a lot of runoff. There were lots of singletons. And this, in a very crude way, suggests that there isn't sort of big areas of chemical space that have now been plugged. What it suggests is that it's a more of a comprehensive process. They're just doing a better job of the chemical name structure recognition and conversion than they were doing previously. So this leads us to sort of conclude, in a short time, ChemAxon has developed a name-to-structure tool we feel that is comparable to its long-standing competitors. And we've shown, I think, that it's improving rapidly. When we use it in terms of the API name-to-structure, and we find that it's got a good range of setting options. It's fairly straightforward to implement, and that's a big overhead. And actually, I mean, speed is one of the key things for us, and that speed that it gets us is really important. We've seen rapid improvement in the more recent versions, and finally, the key message is, in our hands, we showed that 7% of our corpus was only able to generate a structure for those names using ChemAxon alone. And that, I press upon you once again, that reliant on just one structure tool is good. Do you remember that Venn diagram where it's clear that if you're using 4 name-to-structure tools, you're going to, we think, yield an extra additional 40% of structures are going to be converted from their names. So that really wraps it up for me. I'd just like to make some acknowledgements. Daniel from ChemAxon has helped us and give us some guidance, as well as Alex, long-standing, and has helped the relationship. Nico, as you heard, Richard and James are our developers and use the API. Elizabeth is in the audience, and if you're interested, please go and talk to her. We also have a US sales manager who if you're stateside, you can contact as well. And just to give you a way of sort of giving the big picture of where the company's going, Nico was mentioning that in 2010, Digital Science, which now owns SureChem, was released to the world. It's owned by MacMillan, and I do suggest that if you'd like to visit the website there, you can see not only links to SureChem's products, but we as Digital Science have another range of products where basically we're providing, we hope providing technology solutions for researchers in a novel way for the kind of the 21st century. So with that, questions?
Quick one. Did you try only commercial converters, or one of them was a free one?
All the tools were commercial, but in 2011 we're hoping very much that a particular academic name-to-structure tool will be bringing on as well. Opsin. Opsin is produced by the guys at Cambridge. I think it's the Unilever Centre there, under the guidance of Peter Murray Russ's group, and we have real high hopes for Opsin. And if we're making use of improving open access name-to-structure tools, that allows us to not only deliver more sort of product features to our own, but it gives us a much greater way of getting contributions from the wider academic community in, because we realise that this is sort of everybody has an interest in trying to sort out this many relationships that they see in patent literature.
A little bit off topic of question. Did you check at the other mistakes in the patents? I mean, when it is written that 100 molar ratio is used and it is in contradiction with the figure.
In terms of extracting sort of table information or LCMS data, we've yet to accurately associate the chemical names with the surrounding information. So that's a really important part, because what we're trying to move to is a situation where, as a product, as a company, we're able to get relationships between not just chemistry but also the biology and in this case, in your question, the kind of analytical information that's associated with the chemistry. And we want to be able to provide those in a kind of a semantic searchable web interface, but that it poses some real challenges, and we're sort of making some real headway in trying to break the back of that particular problem of bringing on board this other contextual information that's be really useful to know for somebody mining the patent literature.
When looking at the structures that were recognized only by one of the 4 tools, are they more likely to be wrongly perceived than the ones that are recognized by all of them?
So I didn't show you a slide that we performed in 2009, but we actually did some benchmarking, and we felt that actually There are differences in the tools, and we felt that actually tool 1 showed the best performance in terms of that aspect, in terms of the wrong structures. And there is a spectrum of sort of false positive structures, if you like, or structures with errors in them.